below the system is a camera, and that camera is looking up at the eye, and it's actually calculating that gaze point. So the instrument's doing that. But what else is going on is that on the screen, there's a display. There's the screen, and there are buttons all over here. So in one sense, all you have to do is look at one of these buttons, and the computer sees that you're looking at that button, and it does whatever that button does. If you're typing, it's got a letter in it, you type the letter. If it tells you to turn the lights on in your house, it'll turn the lights on in your house. So pretty simple. Eye tracking's done. We can finish the conversation here. Well, we can't finish the conversation here. It's way, way more complicated than that. So let's back off a little further and differentiate these two parts of the system. So there's the instrument right here that's looking at your eyes, and it's figuring out where you're looking at on the screen. So over here, what shows up on the screen is what's generally called the communication software. You push those buttons and the system does what you want it to do. You push a button that says speak, and it speaks what you just typed and so forth. And it's very easy to get caught in the trap of evaluating an eye tracker device by its communication software alone. And the point of this discussion is to show how important it is for the instrument itself to really work well. Not all eye trackers are equal. So they're not equal because they don't treat their users the same. Well, it's kind of funny when I say they don't treat their users the same, but remember what we're doing here. The key purpose of an eye tracking device is to extend the capability of your brain. If you have a disability where you can't speak and you can't use your fingers to push buttons, you have to use your eyes, then your brain has to drive your eyes to do what your hands normally do. And the big problem here is your brain has never used your eyes as an output device. So you're asking it to do a brand new thing that it's never done before. Now, in one sense, it's pretty straightforward. You just look at it. That sounds easy enough. But let's take a special case. Let's take the special case where a person's typing. So they have a whole bunch of buttons on the screen as the keyboard. And you have to look around at those keys. Well, how does the eye tracker know that you're actually pushing a button to type that key? Anytime you look at it, we're going to say, okay, all you have to do is look at it. Well, there's a specification on that. And you have to look at it for a certain amount of time. You have to look at it long enough that if your gaze moves from one key down here to another key up there, it doesn't pick off every key in between. But also, when you finally do get to this one, you don't want to have to wait so long that it slows you down and gets in your way. So the essential goal of a speech generating device is to augment the capability of your brain. And if you're doing it through your brain, we need to understand what the brain does so we can build that instrument to accommodate those characteristics of your brain. So let's dig into what some of this anatomy and physiology is. First off, let's take a look at the eye. So you've all seen this diagram before. Here's the outline of the eye, the cornea, the lens is sitting in here. The iris comes down around the front surface of the lens and creates the pupil right in there. So if you're looking at an object down there, the rays of light come into your eye like this. We'll draw the two rays that happen to go through the top and bottom level of the pupil, and they converge at your eye. And this point source out here shows up as a point on your retina, back in part of the eye. But what do the eyes really do? What's their purpose in this life? Your eyes are mainly an input device to your brain. You kind of get the idea now that we're going to use it as an output from the brain. So we have to retrain the brain to use its eyes as an output device. Well, let's look at some other anatomical properties of your eyes. So when you're using them normally, the way I am right now, and I'm looking at you, I point my eye right at something. Well, how accurately can the eyes point? They can point amazingly accurately. If you look at the retina, take a view of the retina from the back, and here's the center of your retina unfolded, so it actually lies along the inner part of the eye sphere. But if we look at it from the outside, it's got rods and cones all over here. And the central part of your vision is right there, and that central part is the foveola. The density in the foveola is 70 times greater than the density of the rods and cones in your peripheral vision. Nature did this for a very interesting reason. When you're walking through the woods and you got to protect yourself, you need to be able to look at something and examine it in detail when you get close to it. But at the same time, you need to be able to see the entire environment. So when a cougar comes up to your right, then it's not going to, you're going to spot that thing and take evasive action. So you've got these dual constraints of what your brain is doing with your eye. One, it's got to have this huge wide peripheral vision. That's the entire retina. And you also have to be able to decide, now I want to look at something right there. And then you're going to point your eye very precisely. Well, let's look at some of the properties of this eye. And this foveola in particular. As I said already, the density of the cones in the middle of the foveola is 70 times higher than the density out in the outer periphery. Why is that? Because if your eye had this high resolution cone density all over the place, your optic nerve would be bigger around than your head. Nature says, no, that's not a good engineering solution. So what are we going to do? We're going to put really high resolution there and low resolution everywhere. And now our optic nerve only has to be this big around, and it'll fit in our brain just fine. And it'll do the two functions. We can see peripherally and we can see details if we point something. But then what does it have to do? Your brain has to be able to point your eyes. So if I look at somebody over there and look at them, I'm lining this foveola, which is in the center of my eye over here. That foveola is sitting right there. I point my eye, so the new thing that I'm looking at, the image of that new thing lands right on the foveola of the eye. So how big is this foveola? It's tiny. It's 1.2 degrees across. So this whole distance across your foveola here is almost 180 degrees, because you can almost see 90 degrees to each side. But in the center, you've only got 1.2 degrees to look at. So your ocular muscles have to point your eye. When you're looking at something, they have to point it within half of this, within 0.6 of a degree, to actually focus in on that one thing. And your ocular muscle system is one of the most amazing muscle systems in the body. It is the most precise muscle system you have in your body. And for the load that it's got to carry, all it's got to do is rotate your eyeball around in a very, very fluid environment. But it's got to be able to rotate that little eyeball, and those are the 4 strongest muscles, the 6 strongest muscles that you have in your whole body with respect to the load they're supposed to carry. And they are the fastest muscles. Why in the world do they have to be fast? Well, when you look, This now gets into the second part of what your eye does when you look at things. And it's a very strange behavior. But if I look right at you and then I decide to look over at somebody else, one thing I do is when I'm looking at you is I hold my eyes still. And then when I see something out of my peripheral vision that's over there and I snap my eyes over there, that's called saccades and fixations. So if you look at the time behavior of the eye, there's time, and here's one object out in space sitting at this distance and another object in space, we'll fixate on that first point and leave our gaze there for a certain period of time. The next thing we'll do is our brain will make up its mind that now I need to, whoa, something interesting happened in my peripheral vision. I want to look over there, and it'll snap my gaze over there. So bingo, the gaze rotation. This is the angle of your gaze. We'll call it alpha. And so your angle alpha is one value when you're looking at something, and it immediately snaps to another, and it sits there for a while. Why does it have to sit there for a while? Because it's got to get enough photons to get a good image. If you just move your eyes over all the time, you never really get a very clear image. And you certainly don't stabilize that image on the center of your foveola where you want it, because that's what your brain can process with high resolution. So when the eye is still, that's called a fixation. And when your eye moves from one fixation to the next, that's called a saccade. And then this is fixation number 2. This is fixation number 1 in this example, punctuated by a saccade. Well, during a saccade, when your eyes are moving, the image is blurry. It's basically useless to your brain. So what do you have to do? You don't want to waste that time. You're going to look at a bear that happened, or that jaguar, whoever it was that came up, and we need to get our eye over there fast. So the ocular muscles, which are attached to the eye like this, and at the top like that, and a couple on the side, and there are actually some that can roll the eyeball side to side to keep your eyeballs oriented towards the horizon. But these ocular muscles during a saccade, they snap. They just go bam, and they yank your eye over from one fixation to the next as fast as they can, so you don't waste any time. And when it's on a fixation, so that's why it's got to be strong. But when it's on a fixation, it's got to be bloody still. It's got to hold your eye really, really still. Why does it have to hold it still? Because inside this foveola, which is 1.2 degrees across, there are about 100 cones across there. 100 of those babies, which is basically a 100th of a degree. So if your eye just moves around a couple hundredths of a degree, a tiny little amount, a couple hundredths of a degree, it starts blurring the image over those 100 cones. So the design requirement there by nature is be able to hold the eye still within about 2/100ths of a degree. So you got to be able to saccade from one side to the other really fast. But once you get there, you have to hold it bloody still. So nature worked out this marvelous control system for controlling your eyes. And you can now see why it did that. And you can see why you have fixations and saccades followed by another fixation. So what's this got to do with eye tracking? Well, let's talk about one element that is really important that I haven't talked about in this diagram yet. That's these fixations. How often do fixations happen? They occur roughly 4 times per second. So I can glance over fixate for a quarter of a second, and that's enough time to get enough photons to pass that vision, that camera shot, if you wish, back through the optic nerve, back into the visual cortex and my occipital lobe, and your brain can then look at what you wanted to look at, and you can then, it then passes the image up to your frontal lobe where you say, oh, that's not really a bear. I didn't need to have done that. Or, oh my God, it is a bear. I'm going to do something about it. So I wanted to give you this flavor of what the eye is doing and how the brain utilizes the eye. And one other kind of interesting thing to just get the idea that your brain and eye are inextricably tied up with each other, and their behavior is inextricably tied up with each other. So as the eye moves, this timing, this 4 hertz timing, every four fixations per second. And that means that these saccades are basically about 10 milliseconds. They're really short. So your brain is processing these things, and it's got a natural rhythm. It's got this basically 4 cycles per second natural rhythm. When you read, that rhythm's a little slower, but you stop, you pick up a chunk of sentence, and then your brain is figuring out in advance where it's going to look next. And so there's a bunch of text on the screen that's got words like this, and your first fixation hits that chunk of text, and your brain is sitting in the background while you're processing the one fixation, and it's planning the next one. This is all a big planning loop. And it's saying, I want my next fixation to be over here. Pick up this chunk of text. It partially sees some of that out of its peripheral vision. And so it uses that to decide, well, here's the best place for me to put my eye the next time to get the next chunk of text coming in. And then you hear your baby scream. Well, there's all this stuff that you're reading, and your reading task is going on, and you're planning your fixations. But then some other part of your brain, your auditory system, comes in, and it heard the sound. And Wernicke's part of your brain came back and said, that's a baby, and that's my kid. I got to do something about this. So it sends information down to this really critical part of the brain, which is called the superior colliculus. So the superior colliculus, as you might even guess, is right at the center of your brain. It's right in this part of the midbrain. And the reason that it's there is it's been at that location since the beginning of evolution, when we started to become what we are. So it's able to say that this signal that came from your auditory system is more important than the signal that came from your other task, which is reading, and it sends the superior colliculus a stronger signal. And it says, I want the next fixation to be over there. And in your superior colliculus, there's a map that really goes right along with the retina here. And it's, where does the brain want me to look next? So right now, in your current fixation, you're looking at that spot. Your reading says, I want to move over here. Your kid comes over, and your ears tell you, oh, that's over there. So it wants to move the back fixation over there. You can only look at one place at a time. You can only point this tiny little foveola one place at once. It's a winner-take-all strategy. So the brain has this beautiful way of deciding which of these tasks receives the higher priority. And the one that screams the loudest is the one. So the superior colliculus really is building up this map of where it wants the next fit. And you've got spikes all over there for different parts of your brain that want information from the different place. So what I'm kind of getting at here is, again, you see how the brain and the eyes are just integrally connected with each other. Your brain doesn't do much. People that are blind completely reorganize their brain. They use the same brain matter, gray cells, to do the job, but it's very different. And I finally remembered this thing that I forgot earlier. One way that we know that the big clue that our eyes are part of our brains is that the wiring that goes between the optic nerve coming out of the back and the visual cortex back in your occipital lobe and the muscles that get started by the superior colliculus when they decide to put your next, okay, you're going to keep reading, so I'm going to go to this particular next fixation, and they drive the fixation and they set off the ocular muscles into the saccade, which takes you over to exactly that place that your brain predicted it needed its next chunk of information. All those things are inside the arachnoid surface of the brain. Almost everything else goes out of the arachnoid surface to the rest of your body, or from your hands and feet and stomach and back up through that arachnoid surface to get back into the brain. But the arachnoid surface goes out and envelops your eyeball out to about here. And it's got holes in them where your eyeball sticks out. That's out. So there's no arachnoid surface protecting that. It's the brain exposed right to the outside. Well, it isn't, because the real part of the brain is the retina. All this other stuff, the lens and the cornea and the sclera of the eye and all that, all those pieces are really not part of your brain, but they allow the right photons to get in and give you those images that you can process about the world. All right, I've spent a lot of time on the brain, but what's important now for eye tracking is that all of this physiology and anatomy means something when we start to design a system. Remember that we're taking the eyes and then we're now asking them not to be this input device that we've been talking about here, but we're now going to ask it to be an output device. But we need to harness the very same muscular system that drives the eye to pick something with your eyes as opposed to just look at it. We need to have an eye tracker that matches that stuff. One of the things we need to match is we want to be able to click buttons at about the same rate that our eye wants to move around. It sits still for 250, 300 milliseconds, and your occipital lobe says, I got that image, fella. I don't need any more. And the superior colliculus knows that, and it comes back and says, oh, it's time to go to the next, to saccade another time and go to the next fixation. And if we upset that apple cart too much, then your eye isn't going to be happy. It's not going to be in its sweet spot. So when we want to have somebody type, we want them to be able to type as fast as their eyes will naturally go. We can't get there from here. That's too much to ask of the eyes. So maybe it's going to take a third of a second, but you don't want to make somebody wait for a second to look and trigger a key, because if you wait for a second, you will have slowed the whole process down, and that'll just clog it up the works. So we need to drive the system to act that fast. And that in turn has an implication as to how we actually process the saccades and fixations when the eye tracker measures them. We've got something going on at, say, a camera working 60 hertz. We got a bunch of samples here. We might have 1 or 2 samples on the saccade, and a whole bunch of samples up there. But we want to be able to say, oh, you moved into a different key on the keyboard and you stayed there for a certain amount of time and you meant to hit that key because you fixated on it. When you go sliding across a whole bunch of keys, your gaze wasn't still when you did that. You weren't fixating. So we know you didn't intend to hit those guys. But when you fixate, we do know it. But we don't want that fixation to have to last too long. And there's a delicate balance in there. The requirement is that the image processing has to be able to process the subsequent images and say, yes, this is a fixation. Bam, we're going to hit this key. And we can make that decision quickly because we know it's a fixation. We know that it follows the CAD. And so we need to build those degree of smarts into the eye tracker to support this thing called typing. So you all know why typing is important. People have to be able to say whatever they want. You don't want a screen that's full of a limited number of phrases, a limited number of images. You want a screen that's got a limited number of keys because you can't put too many on there. But at the same time, you need to be able to type in anything you want to. And the way people do that is with the alphabet. And you can form your own words. And with that, you're free to formulate in your mind anything you want. The same way that the Broca part of the brain, when you have a thought, Broca's in there thinking, oh, how would I verbalize this? What would I say to express the idea that I've got going on in my head? And then after that signal goes to Broca's brain, it does something else very interesting. And that is, it sends most of that signal back to your cerebellum. And your cerebellum is in control of your speech. If you're talking, it's in control of your fingers if you're typing manually. And this is where somebody's got a disability. We have to get the brain to think a different way. It doesn't make any sense for the brain to send signals to a place, your throat, where it doesn't do anything to your fingers if they don't work. We have to now offload those functions, the cerebellum and the Broca's area. Well, Broca's area pretty much keeps going. It still forms the whole sentence. But we now have to train the brain how to drive its eyes to do what its voice and its fingers used to do. And that's an amazing thought. And in one sense, it's really simple. Just look at it. But it's not so simple. So the next thing I want to do is getting into why it's not so simple. When I'm talking to you right now, I have all these ideas, and Broca's putting together the sentences and coming up with the words, and it's sending converts all that stuff into muscle activity that's going to make me speak. Well, that part of the brain that's actually verbalizing the speech doesn't work for me now because I'm disabled. I've got a disability. So that part of the brain is probably still there, but it doesn't help you actually, the person with disabilities, to actually do anything about it. So what you have to train the brain is to look at something, and you teach them to type. Well, typing with your eyes, in one sense, is a marvelous thing. If you can't speak and you can't use your fingers to type, it's wonderful to be able to get your ideas out using any words you want by typing with your eyes. Bingo. But now let's put ourselves in the shoes of somebody who's actually trying to do this. So I have this idea up in my frontal lobe cerebrum. That data goes to Broca's area and it starts putting words together. And then instead of just sending the signal right through the rest of the part of the unconscious brain that just comes up and has the words come out of your mouth, then what happens? Well, if you're typing with your eyes, the first thing you need to do is break the sentence down into concrete words. And then you have to spell each word out into its individual characters. And then you need to consciously drive your eye to each of those letters in sequence. And this all leads to cognitive load. It really puts a tremendous stress on your brain for you to do all that stuff. And my heart goes out to people who have disabilities and have to type with their eyes. But we also have to design an eye tracker that makes it as easy, given all those constraints that any eye tracker has. We want to minimize any of that issue and make it as easy for people to do so they can type as long as they want to and not just get driven to the point where, okay, I gotta quit. So this is the balance that we're trying to achieve. And the important part of this is designing the system, an eye tracking device to pick it up. So we've already talked a little bit about being able to pick up the fact that you've got intentional saccades going on by analyzing the path of the eye. Key point. The only way we can analyze this path accurately is if we have really accurate gaze tracking. If we've got noisy gaze tracking, these samples are jumping all around and those samples are jumping all around. So if you go from one fixation to another fixation that's where the noise between the samples is as big as the fixation itself, it starts not to work very well. And the standard eye tracker, the way they solve the problem is they smooth over a longer period of time. Smoothing over a long period of time slows you down, and we've been through that and why the brain hates it. So a really important characteristic of an eye tracker, the instrument that measures your gaze, is it's got to have extremely high accuracy. Another thing that we talked about was we want it to be fast. Well, here it's a little subtle because speed in this case is not necessarily how many samples per second your eye tracker is running. You don't have to get up to 100, 200 hertz or anything like that to do it. All we have to do is have the eye tracker, the accuracy over about 10 samples. And since fixations are typically 250 milliseconds each, 10 samples is 25 milliseconds. 25 milliseconds is only 40 hertz. We don't need to sample any faster than that. We need to make sense of the time signal faster. And that then becomes a significant problem of eye tracking design. And if you're really able to smooth it, you can do all kinds of eye tracking applications and smooth the data, and it looks beautiful. But it's not going to be really enable somebody to type fast for many hours a day without getting tired. So accuracy and speed are two really important factors in eye tracking. There's another that's very important, and that's tolerance to head motion. And tolerance to head motion, what that means is that the camera, the eye tracking camera, has a wide field of view, and you can move your head all over in that head box or that field of view or whatever you want to call it, and it still tracks your eyes great. But there's a classic problem in eye tracker design, and that is the trade-off between accuracy and freedom of head movement. In order to get a good, clear image of the eye and measure its properties really carefully, you want to be able to zoom in on that eye, expand that image, if you widen the camera field of view out, then the pixels actually have to spread out. Interesting note here. The camera has this uniform distribution of pixels all over its retina. It's not like our eyeballs that have this really high resolution at the center. So what we'd have to do if the camera were an eyeball is the camera would have to rotate around, point directly at your eye, and then it could get this nice high resolution image. And one day that's going to happen. We're going to have cameras rotating around that are going to be able to zoom right in on your eye, no matter where I'll move my head, just like your eyeballs can rotate around in their head. The eye tracker is going to move around and follow your eye and get those high resolution images that give us the accuracy we need. Today, we don't have those. So one thing I want to say about the eye trackers that iGaze Inc. makes, the iGaze Edges, they don't have very much freedom of head motion. And in one sense, that's a problem. But what we've chosen to do over time is favor accuracy as opposed to the freedom of head motion. And what we have found over time, and this is basically because Nancy's been doing a lot of research out in the field. I'll talk more about Nancy in a minute, but she brought back a lot of data that showed that people that were able to utilize the accuracy and speed were able to do such things as write whole books with their eyes, spell out every damn word in a whole book. They had the patience to do it because the system was matched to their eyes. The alternative is to widen the field of view, and you get all kinds of freedom of head motion, but almost one for one, if you increase the volume of the head motion by a factor of 2, the accuracy goes down by a factor of 2. And we found it's very important to keep the accuracy because people will then use their system. They'll get up in the morning, they'll use it all day long, and they'll be happy. And when you don't have that kind of accuracy, you get fatigue much faster. You start making mistakes when you type. Your brain gets slowed down, and it basically says it's quitting time much sooner than if you have a high accuracy system. So that's why we did that. And what's the downside of that? Well, one of the big downsides is that people, when they first sit down and operate a high accuracy eye tracker that has a narrow field of view, have a problem. They have a problem for a couple of reasons. One, they have a lot of natural head motion. And you don't want to tell them, no, hold your head still. As soon as you tell them they got to hold their head still, they're off the track. They're not trying to learn eye tracking anymore. They're trying to accommodate the limitation of the eye tracker, and that turns them off. So that's a problem. And people with CP, for example, can't hold their head still. There are a number of people who can just sit down in front of a system and start using it pretty much right away, and that's cool. But a lot of people have the tendency, because your brain hasn't learned how to really point your eyes yet. It knows how to point them, but it doesn't know how to point them in response to this task of eye tracking. Those people want to move their head too. They're thinking, oh, if I'm controlling something with my eyes, the way I look right is to move my head right too. And they just put those two together because that's what we do every day. If I want to look far left, I won't just move my eyes to the left, I'll move my head with it. And if people do that, they're going to get out of the field of view of a narrow field of view camera, and it's not going to work for them. So it takes a little bit longer for somebody who has this problem to learn that it just doesn't matter. You don't have to move your head. You just need to let that go. But it doesn't, people don't learn it instantaneously. So when they're getting evaluated, they'll move their head around, they'll go out of the field of view, the eye tracking stops. And so the general conclusion is this system doesn't work for my client. And they move on to another eye tracker. And that's too bad, because if they just played with it for a while, it's not that they have to learn to point their eyes. It's that they actually have to just sort of unconsciously learn, you don't have to move your head. You're allowed to just sit still and move your eyes, and that's all you have to do. And once you do that, the accurate eye tracker really swings into play and makes it a lot easier to go from there. So that's basically what I've got to say to you guys. It's pretty cool. Yeah.
All right, so the first question goes back to the idea of having an eye tracker, a gaze duration be fairly quick. And the question is, what if it's someone who has a cognitive deficit of some sort because of a brain injury? Should the tracking speed be slower? Should it be as fast, or should it be slower due to some sort of slower processing, or maybe anything you could talk about along those lines?
Nancy's really the right person to answer this. Nancy's in the room here. She's my wife, and she's an ex-emergency room nurse, and was really crucial to the early development of eye tracking here at iGaze Inc. She was the one who had experience with people who would come in with these accidents that were going to require something like an eye tracking device. She went out in the field and worked with these people. She saw very clearly people who have disabilities also often have problems with their eyes. And she brought back the images of all these people who had problems with their eyes and dumped it on my desk and said, Dixon, make the system for that work for that. And we were pretty good. We picked off a lot of those, not all of them by any means, but we've done an awful lot about special cases. And Nancy has developed what we call the medical model, and that's her term. And it's based, that a lot of what I've been talking about here is how do you design the instrument, the eye tracking instrument, to best medically accommodate what the eyes really want to do and maximize the output.
Good. Next question. Thank you. Next question.
Yeah, Nancy, you want to come up and answer that question?
Pull the mic off.
That's okay. Now, wait a minute. I'm going to be 1 minute. This is a really common question.
Get right up close to the mic, so everyone can.
Okay.
Pull that up.
Sorry, she's my wife, so she can
I
get
wasn't
close.
supposed
But
to do
this is my.
Okay. The reality is, because of the fatigue factor, you don't want to force somebody to fixate for a long time, because that person who's already struggling with cognitive issues is going to get worn out fast. So what you want to do is keep the gaze duration, how long you fix, short. And then in the image processing within the eye gaze system, what we do is expand the amount of time for the saccade. So when the person is moving their eye more slowly because of cognitive issues or even physical issues, they can take all the time they want. It's a setting that can be played with and adjusted. And then when they finally get to where they're going and stop, then the system responds. Because what you don't want to have happen is slow down the whole system, and then the person's eye is moving slowly and then it stops. And now it's struggling to stay still long enough for the system to understand that's a fixation. So when you mess around with a fixation, when you force somebody to hold their eyes steady for a long period of time, it's exhausting. It's like saying, okay, hold your breath to trigger this. our eyes saccade and fixate, we don't think about it. And you don't want to mess with that if you don't have to. So you don't want to increase the whole time it takes to type a character. You just want to increase the delay from one character to the next to give that person time to process and move on. And we typically change the incremental time by maybe 1/10 of a second. So we start out with 1/10 of a second extra added on to the saccade time, and we can go up to 1/2 a second or more, but you have to do it slowly because it gets cumbersome if the person has to wait for something to happen. Okay, that's it.
In the meantime, people are learning where the keys are on the keyboard. They'll stop and think about something. They'll fixate when they really don't want to hit a key, and it takes a while to get used to this speed. You have to. It's somewhat like riding a bicycle. You can't ride it too slow, but once you learn how to ride, you never want to get back on that tricycle.
Great, next question. This question is asking, how readily can eye tracking accommodate corneal diseases that distort the surface of the cornea, for example, keratoconus, or I know corneal scarring, or maybe other disorders of the cornea?
We can handle that pretty well. The calibration system in the eye gaze edge is able to handle a lot of irregularities in the eye. We can handle fairly severe astigmatism. There's a thing called flattening of the cornea as it gets out towards the edges. And when the actual lens and the cornea atrophy some, that gets pretty severe. It's not a sphere. And we have to make sure that we're modeling the eye as something more sophisticated than a sphere. And we've got about 6 parameters that we can vary, and we'll pick that up in the calibration procedure. That does have the issue. It's sometimes harder to calibrate all of those parameters. So, but once you've done it and got that calibration, then it works quite well and accommodates a lot of those things.
Great. All right, next question says, I'm hearing, this was a while back, I'm hearing that the head window or the head box is inversely related, the head box size is inversely related to accuracy. Is there a way to adjust the head window size for each individual in different eye gaze systems? Or is that predetermined based upon the hardware or software that arrives? Most eye tracking systems that I have used have a preset place for the head to go 22 inches from the screen within the square, left, right, up and down. But I'd love to be able to change it if that would make it more effective.
That's a marvelous idea. That's really, really a terrific idea. And we've actually played around with that in the lab some. One thing that when you have something adjustable like that, you need to be able to measure the adjustment that you've made. So one way you'd think, well, I'll just recalibrate, make the adjustment and then recalibrate. Well, that doesn't entirely handle the situation. There's a lot of sophisticated equipment in there, and we're working on that kind of thing, but we don't have it yet. And maybe other eye tracking companies are working on that idea as well. I don't know of any.
All right, next question. Have there been any fMRI of proficient eye gaze users changes to the brain that you know of?
I don't know of any. I think that would be marvelous to do fMRI studies to see how those brain waves seem to change as a function of what you're doing. And particularly if you could get longitudinal data on this, you see somebody when they're first sitting down in front of an eye tracker system and you take their fMRI and you record how long it takes them to calibrate, how fast they can type, what their typing accuracy is. And then every couple of days, you take some more samples, and as that person finally figures out what he's doing and takes what he's learning consciously and gets his unconscious to take care of those issues, it'd be wonderful to see that on an fMRI study, but I've never seen anything like it. Cool question.
And then I had a question. You were talking about when somebody has an eye tracker that has a smaller head box size, there's a limitation because they might naturally move their head or neck. How do you teach, say if it's someone, an able-bodied person who does not have CP or is not locked in where they're not moving, what would you say to teach someone, or how do you teach someone to get in that zone pretty quickly so it's not as much of a challenge?
As far as I can tell, the best thing to do is just tell them, hold your head still. You don't need to do that. But there's controversy on that. Nancy's sitting over on the other side of the room right now saying, no, don't do it that way. So I'm going to give you an alternative answer to this question.
Okay, so as soon as you say to somebody, hold your head still, they're not focusing on the screen and how their eyes are working. They're focusing on holding their head still. So the alternative to that is to have a sweet spot. If someone is trying the system for the first time, be sure that they have some place to place their head. So if they have a wheelchair with a headrest, the head goes on the headrest so that as they calibrate, that's where they're calibrating. After calibration's done, if they start moving around, that's okay. When they go back to the sweet spot, when they get back to putting their head where it was, the accuracy resumes. So this system tracks. If you move out of the field of view of the camera, nothing's lost. If you move back in within probably 1/10 of a second, maybe less, it reacquires the eye and resumes operation. So for a good user, they may not even be all that aware that that pause has happened. Interestingly enough, when we started 30 some years ago, ours was the only eye gaze system for people with disabilities. And I worked with a lot of kids with CP who really struggled some to stay still. And what I learned over time was once they learned to separate eye movement from head movement, those issues pretty much go away. It's two separate functions, but you can't really say to a young child, you got to do this, you can't do that. But you can say to a young child, here's the sweet spot. When your head's there, this system is going to do what you want it to do. And a good quick test of whether that's possible or not is, what does that child look like watching television or a video? If they're able to, when they're relaxed, lean their head against the wheelchair and focus on the screen, and they're not moving all over the place, they can do the same thing with eye gaze once they've learned the skill of separating the eye movement from the head movement. It's a really interesting process to watch. I've worked with some kids that you would say, there's no way they're ever going to be able to run that system. Two of them went on to college, started out as young kids and went all the way through school. So it's possible, but don't say to somebody, hold your head still, particularly holding your head still in free space. Nobody can do that well at first because we all lean into our computer screens as we're working. We don't even realize it.
Thank you. Okay, next question from Crystal says, can people with strabismus use eye tracking?
The answer is mostly yes. Not all people can, but the answer is mostly yes. And what happens is that when somebody has strabismus, their eyes are looping around, their gaze is looping around. But there's one part of that cycle that fairly reliably comes back to a certain point. And we have to do a fair amount of learning and optimization to get that to happen. So we recognize which part of the cycle we actually want to do the tracking on, because what happens is your fixation will generally go right where it's supposed to go, and then your eye will drift and then come back and drift and come back. And those are fairly repeatable patterns in people. And if you know what those repeatable patterns are, you can predict where the eye is going to go. And if the eye does in fact go where you're predicting it, then you can say, okay, this is the same fixation. If all of a sudden it takes it off on a completely different path, that means that your superior colliculus told the ocular muscles to saccade and move to a different fixation location. Having said that, I don't think that we've got an off-the-shelf solution that you can go put in front of somebody right now. But here again, she said strabismus. Other question?
It looks like that. Those are the only questions. We're rounding out the hour. This might be a good time to wrap up.
Sounds good. Well, the last thing I'd like to say is that Nancy has given a TED Talk. And she talked about a lot of the people that have used our system over time, sort of a whole bunch of case studies. And if you want to look at that TED Talk, just say Nancy Cleveland TED Talk on Google and you'll find it.
Put it in the chat right now.
Well, thank you guys very much. I always enjoy these sessions. It's fun. I kind of wish you were all here in the room and we could make eye contact with each other. After all, this is an eye tracking topic. But have a good night, everybody. Thanks very much.